So whenever we're talking about anchors, we're talking about either single point or multi-point anchors. This becomes really important in the rescue world because we can end up putting substantial forces through our anchors. So we have the diagram of the percentage force increase as we work towards our internal angles, but we do it fairly practically so we can see what it means to us. So if I've got a single point anchor, and I put my body weight on it, cool, so that's just my body weight. I'd like to point out I'm wearing a harness as well. So a single point anchor has got to be unquestionably sound. And in practical terms, that means we're looking for an anchor that's a minimum of 12 kilonewtons, roughly 1.2 tons in a static load. So examples of single point anchors, they can be pre-installed in the infrastructure into the building itself, or temporary solutions that are hired or bought in. Things like bolts, structural steel, they can have holes in them, potentially shackles in them. As long as it's a rated, tested anchor point, we can use it. If our single point anchor isn't unquestionably sound or doesn't reach 12 kilonewtons, we're going to need to use a multi-point anchor. So at least 2, can be many more. And we're going to try and share the load between those anchors. And this is where our internal rigging angles become important. So in this example, when this is loaded, my internal rigging angles, the ropes are going to be pretty much parallel, so we call it 0 degrees. Obviously, this is a bit more real world, so it doesn't quite work out like it does in the PowerPoints. So there we've got 36 and 40. So think back to our single point anchor. What I've done now is effectively share the load, my single mass, between the 2 anchors. So I've broadly halved the load on each anchor. Okay, so now we've widened our anchors apart, and when this is loaded, this is roughly 90-degree internal rigging angle. There we are. So now we can see 51, 54. That's increased the load I've put through each anchor. And mathematically, we're looking at about 71% of that single mass on 90-degree internal angle. So I've opened my anchors up again. They're even wider. So when I sit on this, the internal angle is going to be roughly 120 degrees, which is what we call the critical angle. And then we can see 78 on this one, 75 on this one. The single point load was 78 kilograms. So we can see on each anchor, we've now got 100% of the load. So we can see with our anchors close together, we're sharing the load. As our anchors go further apart and we're increasing the internal angle, we increase the force on each anchor out to 120 degrees, the critical angle, where I'm putting 100% of the load on each of my anchors. If we go over 120 degrees, we now start to get force multiplication. So we know if we go over 120 degrees, we're going to get force multiplication on the anchors. So we try and avoid it. That's not to say we can never do it. Stuff like a horizontal lifeline or a no-space anchor, we know we're taking these ropes way past that 120 degrees. But we have to have the appreciation of what that's going to do to our anchors. So we know in a single point anchor, I put 78 kilograms on the anchor, and we know through sharing the load, we shared that down. So when we first rig these, they look like they're 180 degrees, but because the force we put through and rope stretch, that internal angle always comes down. So from my 78 kilograms in a harness, we've reached 127 on one end, and 120 on the other. So you can see how we've got force multiplication on the anchors. So similarly to internal rigging angles, we can have a difference in the force on our anchors when we deviate the forces as well. So we'll just look at the two opposite ends of the spectrum here. So this rope isn't deviated, so there's a 0 degree deviation. If I put my weight on it, I've got heavier, 79 kilograms. So now I've gone to the other extreme, I've got 180 degree deviation. So if I put my weight on it, so having loaded the 180 degree deviation, I've now put 137 kilograms through this anchor. So I've doubled the force on the anchor. That's not to say we don't deviate, but we have to have an appreciation that from 0 degree deviation is the straight load, all the way through to 180, we progressively increase the force we're putting on our anchors. Right, so when we come on to multi-point anchors, there's a couple of rules of thumb that we try and follow. You can use a couple of different acronyms to help. READS, or some people use IDEAS, does the same thing. So READS, we need some redundancy, we need some equalization, we need to look at the internal angles, we need to look at the direction of the load, and we need to do a systems check to make sure everything's screwed up and safe. Okay, multi-point anchors, anything more than a single point. So in this case, we've got 2 rated ground anchors, and we're going to rig using both of them. So figure of 8 into 1, work out my direction of load, tie my equalizing knot, an independent knot, alpine butterfly in this case. Test it for the direction of load. So actually I want to come this way a little bit. There we are, so that's now exactly where I want to go. And now I can apply my reeds. So I've got my strands here, 1, 2, and the resultant direction. Redundancy. So if any one of those failed, have I got redundancy in the system? Yes, because I've used 2. Equalized. When I pull on here, is each strand taking an equal load? Yes, it is. Angles. This internal angle we spoke about before, is that acceptable? It's well below 90 degrees, happy with that. Direction, it's equalized in the direction I'm going to be working. And then a final systems check, screw gates, knots, everything's good to go. So to summarize our anchors, single point anchor, unquestionably sound, or at least 12 kilonewtons. If you're in the rope access world, you're looking at 15 kilonewtons. Multi-point anchors, any more than 1, 2 and above, and that's when we apply the READS or IDEAS principle, checking for the redundancy, equalization, internal angles, direction of load, and a systems check to make sure everything's screwed up and safe.